In the last video, we saw the single control driver pattern. So one CPU driver orchestrating worker groups across GPUs. That was all conceptual, and in this video, we'll start building it. We'll start from zero and learn just enough array to do what we want to do. And by the end of it, we'll have gone through the notion of worker and basics of it with an identity, a topology, and a composable merge registry and guaranteed placement. So let's start with basics of Ray. As you can see on screen, I installed Ray. I think with the current version of Ray, it doesn't work with Python 3.14, so you have to use 3.13. And let's get started. So we start with the most basic thing that we'll have to use later on as well. So init here does connect you to a cluster. It creates one locally if there isn't one, or connects to an existing cluster, and we'll do that later on. We'll connect to a cluster with GPUs. Here I'm just on my Mac laptop, and I don't have one, but let's see what kind of resources we have. So array allows you to do that with cluster resources. And if we run this, we'll see what will happen. As I said, array.init starts a local cluster on your machine, and later on we'll use a Slurm setup, and we'll see how that goes. So here we'll see some stuff. When is ignored, ignoring to upload to cluster for these files, etc., etc. So what's happening here is that Array is detecting that UV is managing the environment. It detects the parent process with PSUtil. So it packages up the working environment, including the PyProject atoml, etc., into a zip archive and uploads it to Ray's internal storage. This is how remote workers create your environment. But this is not very important for local dev, and you will see that if we activate this and run it with Python instead, it should not show the same thing as before. Here, array.shutdown is not necessary. I'm just having it for good hygiene. But since our script exists anyways, Python will clean up anything. So you'll see that we don't have the same logs as before. And here we see that on my Mac laptop, I have 10 CPU cores. I have here the memory. So this is a heap memory that Ray can use for worker processes. And this object store memory is, we'll see that, but the object store memory here is the shared memory between workers. Like when you ask a worker for a value, it will be stored there before you get it. And then we have a node here. We only have one node. We have a local cluster here, and the internal head says that this is the head of the cluster. So let's get with some basic thing and see how Ray works. Let's start with the notion of remote functions or tasks. And this and the notion of actor will be like the building blocks that we'll be using for everything else. So a remote function goes like this. Maybe let's try some very basic thing. Gets decorated with ray.remote, and then you can call it like this. So remote, and you put your arguments values here. Let's say 1.1. So let's say what this gives us. So ray.remote, the decorator tells Ray this function should run in a separate process, not on this process, not on this thread, but in a completely different process, potentially on a different machine, and we'll see that later on a Slurm cluster. So as you see here, we don't get 2 back, we get the object ref. So this is a future. It's a handle to a value that doesn't exist yet. But it does, well, it does exist. This is very fast, but it lives on another process. So in order to get the value, you have to do array.get. Let's print this. Array.get future. So array.get blocks until the result is ready, and then it puts it back to our process, and we can visualize it or do whatever we want with it. So this is the fundamental pattern we'll be working with: that remote to dispatch and array.get to collect. And every interaction with Ray with workers will go through this pattern. Now, let's see parallel tasks, how we can do them. We can do something similar. Say 100. And if we want to get the results, we do array.get futures, and we can print it. So with array, all the tasks do launch immediately. But as I said, this is blocking, and array schedules them across the available CPUs in parallel, and then we collect the results afterwards. So this is like this pattern here we'll be using it a lot in order to dispatch different data to different workers and different work in general. So now let's look at what are actors. So as you can see here, the function or like a task or a remote function doesn't have state. It's stateless, and every call to the function that's remote is independent. There's no shared memory between calls. But for our workers and for like mostly every complex work you'd like to do is to have some kind of state. For example, you want to store GPUs in, you want to store weights, model weights in GPUs, stuff like that. And this is what Ray calls actors, and it's very simple, and it looks like this. We still decorate, but you decorate with array.remote, but you decorate a class instead. You can give it a counter if you want or not. Give it a constructor or not. Well, it's not really a construction in Python, but get the gist. And we can have something get state to see that it is indeed like the state is indeed persisted. So here when we decorate with array.remote, this decorator is applied to the class, and it also means that it's applied to every method in the class. And when we call the class.remote, the object will remove in its own process, will be living its own process and hold the state. So it's like if this init here is running a new process, and every new method call is sent to that process instead. So if we do counter, and here we can pass the arguments to the constructor. Let's say start equal 10. And if we want to call the methods, we do similar as before, increment dot remote, and we can look at this value, and we can also try and do something like this, futures, or like it's not even important to do it. Mode for in range 9, and then get state that remote. So as I said, this pattern will be used in a lot, and you will see it more and more. And the more you use it, the more you get familiar with it. Classic errors here. So when I'll move on to the cluster later on, I will be editing this kind of errors because submitting stuff on a cluster takes time. But Yeah, so as you say here, as you see here, we incremented it, and the state we incremented later on, and the state is indeed persisted. So these are the basics of array we need, and everything else will build by ourselves. And let's get to the Slurm cluster. Blah 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 blah. So I'm back on the Slurm cluster. Quick context on Slurm: it's a job scheduler. You describe what resources you want in these headers here that we have here with sbatch, and like how many nodes you want. Here I'm asking for 2 GPU per node. I'm asking for for 4 800s, number of CPUs per task, etc. And the scheduler here, Slurm, puts you in a queue. And when resources are available, it gives you the machines. So I'm not a specialist on Slurm, but one thing that matters for us is that Ray doesn't know about Slurm. So by default, the Ray-init we saw before, this one here, creates a local cluster on the login node, which has no GPU. So we need a small script, which is this one, that starts array cluster across the Slurm allocated nodes, and then our Python script will be able to connect to it via ray-init. I won't go through the details here of this script. It's just standard boilerplate, but the result is when our code runs, Ray already knows about all the nodes and GPUs. I'm gonna remove this one. There are some headers that I don't really want to show, but that's it. And when it comes to the versions I'm using for everything, so it's here in case there's for reproducibility. So let's get started so we can actually print the resources again. Ray.cluster resources. And I know that there will be a key called GPU that we can get. So maybe I can just show that indeed we have the number of GPUs that we are requesting. Now use and this. So to launch this one, we do sbatch launch.h, and here I have like a command to launch this file after activating the virtual environment, etc. So it will put it in a queue, and I will have to wait. I don't know how much I have to wait, but you see here it submitted the job, and I will cut so that I can show you directly the result. And also I will be making mistakes while coding live, but then I will edit them obviously so that it reduces the time you have to watch. So I'm back. You can see that the accelerator type we have a hundreds. We have 64 CPU cores, so we ask for 32 per node. We have 8 GPUs indeed, 4 per node, and we have this node and this node, so 2 nodes. So now let's put a worker on each node. I just remember that I want to talk about it, but I keep using the worker term instead of actor. So Ray calls them actors because I'm afraid of getting them confused, or maybe the viewer will get them confused with the actor from actor critic. So I will be using the term worker for Ray workers, for Ray actors. So let's get started and see what we can do here. Let's have something very simple. We'll put a process in every GPU, and let's ask it for information about itself. We'll introduce here something new. It's GPU is equal 1. I can explain it later with the different information I want to return. I want the worker to show me its host name. We'll see that every 4 workers will have the same hostname since they will be on the same node. Let's see the process ID. Let's see the GPU ID as well. I should import the libraries for this. I can also explain this later on. CUDA visible devices, and we can see the GPU name as well. So for this we need a torch, and for the host name we need the socket library. I believe this is the name, and we can import them here. And let's start them on every GPU here. So num GPUs equal 1 here. What it does is that it gives exactly to each worker one GPU exclusive to it. And Ray, what it does is it sets this environment variable to that GPU's physical index. So let's say we are on this node. We have 4 GPUs. They should be indexed from 0 to 3. And CUDA visible devices, it's like it's selecting a subset of these GPUs. So which GPUs are visible to that process. And if you set CUDA visible devices here for 0, so that means this worker will only see that it has access to the GPU indexed by 0. And from PyTorch's perspective, there's always only one GPU because that's what it's visible to the process. So actually, for PyTorch, it's always gonna be CUDA double dot 0. And this is why this works regardless of which physical GPU the worker lands on. And for a GPU ID here, it's gonna show us the physical index of the GPU, and the host name should show us the node. So let's get these worker starters. As I said before, we'll be using that pattern a lot with that remote and ray.get to get information. We have no constructor here, so no parameter to pass. We know that we have 8 GPUs. Each worker is requiring exclusively one GPU, so we can get them. And here, what we can do is for every worker, we can ask for who is that remote. Again, no parameter here, and we can print that. Call it identity, though it's not really identity, and I will make something better later on. But we can run this and see what it will give us. I'm back, and you can see here every worker is printing its identity. I had to correct this mistake. As I said before, I will be editing this kind of stuff. It was a float. So for every worker, it shows this is the host name, and we have 4 here and 4 here. It makes sense, and this is what we expected. And again, the nvar of CUDA visible devices makes sense. It goes from 0 to 3. We have 4 GPUs, and the GPU name is this. So these are the less memory, 100s instead of 80 gigabyte. So we can see here that for every worker is on a GPU, etc. But here's the thing. This worker here, for example, it has no idea that it's the worker number 4 out of 8 workers. It knows it's on some GPU on some machine, but it has no rank. Rank, it is like its global index in terms of this world. It doesn't know what the world size is. It doesn't know there are other workers at all. And more importantly, and what we care about, there is no way to talk to other workers. So if we are here in this worker, there is no way to access or share information with all the other workers. We do that with torch.distributed, and torch.distributed needs a rank, it needs a world size, and it needs a rendezvous address to initialize a process group. And the workers can't figure this out by themselves. We have to give it to them, because there's no shared state. There's no way they can figure it out. There's no shared state. There's no leader elections. There's no file system convention or anything else. Ray just spawned them on arbitrary nodes, and they don't even know there are other peers. The only entity with a global view is our driver script here. It created all the workers, it knows how many are there, so the driver has to be the one to tell each worker who it is and how to reach the others. And so that's what we'll do. So this will be our main goal for this video, and it goes through torch.distributed. Torch.distributed is what will create the communication between the different workers, and we will prove that indeed it works by doing a very simple torch example of an AllReduce across the nodes, across all of these different workers. So we want our workers to do GPU to GPU communication. For that, we need torch.distributed. Obviously, you can use other libraries. And specifically, we need nickel. So it's typed NCCL. It's NVIDIA Collective Communications Library. And as the name indicates, it's NVIDIA's library for collective GPU operations. But before any of that happens, the worker needs to find each other and agree on who's who. That's called a rendezvous. Because otherwise, there's a kind of chicken and egg problem. Workers need to communicate to set up communication. They are on different machines. They don't know each other's addresses. They don't know how many peers there are. So in order to break this cycle, we need a rendezvous point, a known address that every worker connects to. And then they will all show up there exchanging connection information. And after that, they can talk directly. So this is a basis of the identity of a worker. So its identity will be the rank, so its unique global ID, which goes from 0 to world size, in this case from 0 to 7. This is how workers can identify each other in collective operations. The world size is the total number of participants in these collective operations. Everyone needs to agree on this so the rendezvous knows when all workers have joined. That's very important. And we need a master address and master port. The master address is the IP address for the rendezvous point, and the master port is just a free port on that address. So you can see that here and here that the rank is just our loop index and nothing more than that. Worker 0 gets rank 0, worker 1 gets rank 1, etc. Later on, we'll be able to control that more precisely, but for the moment we don't really care. For the world size, we know that it's this number of GPUs. We have 8. But what do we do for the master address and master port? There is nothing really that says what we should do about them. We can just take a convention, and our convention will be to take the one from rank 0. So let's go and add 2 methods on the worker class. We'll get a get IP method, and we'll have a get free port. So for the IP method, we'll use it in order to get the master address. So this method will be calling on worker 0 here from the loop, and get free port here. The goal of get free port is just to open a socket to bind it to port 0, and then the OS picks a random available port and return it. Bad. And here now we can come to a worker 0, as we said, just our convention. Let me comment this. You can also remove this. We're gonna say that our master address is workers 0. We can call the get IP here. I believe I called it get IP. And similarly for the master port, get report dot remote. And our rendezvous point, what will it look like? As I said, is just an address for the different workers to meet, so they can agree then on communication. It will look like this, and this is literally what will be given to something like torch.distributed.init process group. So in each process group, it will take a rank. So in our case here, it's just the loop index. It will check the world size, which is the number of GPUs. Let's say rank index, loop index, and it will take master address and master port. We can have that as a method on every worker. We can call it something like a worker.distributed, and that's it. And similarly, we do rate that get. Since we need the index there, we can do enumerate. We can create this method here. If I called it distributed, which will take the rank, it will take the world size, and it will take the master address and master port. And what it will do is basically just torch.distributed.init process group. This we can import as dist to make it easier to use. And then we have backend. We have to give it to init process group. I forgot to talk about that. Rank is just rank, and the world size is the world size. And here, the init process group takes an init method, which is just this. Let's put f here, and that's it. We can set that rank here as the rank. We'll reuse it later on. It's not necessarily to do that, honestly, but since I will be using them later on, I'm saving them. And that's it. So the driver will call this on every worker here. And honestly, we don't even need this. And so it's gonna pass all these arguments to every worker, and it's gonna init the process group. So each process group here is going to do the heavy lifting, honestly. Its backend here is nickel for the GPU to GPU communication. If we were doing CPU communications, for example, CPU only, we'd use glue, for example. You can find a lot of backends on PyTorch documentation. So what the init process group does here, it does three things. It connects to the rendezvous address. It waits until all world size workers have joined, and then sets up the nickel communicator so that GPUs can talk directly to each other. And after this call returns, the worker can participate in collective operations. That's nothing. It's not very complex. One thing here maybe to say about this is just from the driver's perspective, it's creating all these workers. It asks for worker 0 for his IP for a free port, and then it creates all the different workers and then sets up the communication for them. And it blocks inside each worker until all world size workers have connected to the rendezvous point. It's very important. If we called, it's important that this happens in parallel because if we did that sequentially, it would not work. It would hang because first worker would have to wait for others to join in. But since it's a blocking operation, they would never join there. And in order to prove that this indeed works and these workers are able to communicate, let's do a very simple AllReduce operation. We can call it globally. It will be an AllReduce among all the workers. We can have just something very simple as a sum. So this is the tensor. Well, that's why I wanted to have here the rank, so that I can just reuse it. And we can save the value here so that we can print it later on, so that we can show that for every worker the value before and the value after. And here we just do AllReduce, the chancellor that's participating in the operation, and we do sum. And we can say that after that item, we can print the rank as well. And similarly here, let's call it results, array.get, and here we do what do they call it, this that remote for in workers. So this should be enough, and it shows how easy it is to, like, from this single driver, how easy it is to send different information or different data and set up communication between different workers and orchestrate them. And it's just a matter of putting the pipeline together. Let's print it. So what it should show that for every rank, the before value should be 0, 10, etc. And then the sum should be the sum from like 0 to 70. I believe it's 280. So I will launch the script again and come back when it's when I have the results. I'm back, and as you can see, the before values for every rank, they make sense, and the after values as well, they show the AllReduce with sum. I would like to take a moment to talk about something. So the why this works, by the way, is because Ray will launch like methods sequentially on actors. So if we launch like, so this is scheduled after this one, and since this one is blocking, since this blocks, it lets us have correct result. But if we did something like here, we wanted to do some computation that we'd give to this for some reason, and this computation is independent to workers or something, or like if you just wanted to print here like done communication established, this will fire immediately, and if you want to block that, you can do ray-get, and that's it. One other thing I'd like to explain, I was taking some time going through the code while waiting for the results, is why here we have CUDA, the bicycle CUDA, without specifying which GPU exactly, is because the array handles the GPU assignment. When the array spawns workers with num GPU equal 1 here, it sets this variable CUDA visible devices, right? I don't think I have the, yeah, I don't have the my prints anymore. And it sets that environment variable in the workers process to a single GPU ID. So from the workers process, there's only one GPU. It's CUDA 2.0. The worker doesn't need to know it's actually on physical GPU 5 or whatever. Ray abstracts that away. So let's improve our code a little bit, because init.distributed here takes 4 loose arguments: rank, world size, master address, and master port. And we haven't even included local rank and local world size yet for intranode communication. And we'll need that later on, and we'll do that. And it's very much needed for knowing things like which TP, like transfer parallel group the worker is in, etc. So it's at least 6 arguments. And as we add more information like topology, it will be more. And passing all of that as separate arguments is fragile. It's easy to swap orders, easy to forget some, and yeah, and the worker stores them all as separate attributes here. So what we really want, and this is gonna be like the identity I talked about before, what we really want is a single identity object, ideally immutable, and that contains everything a worker needs to know about itself. You pass it once, and the worker stores it, and it's done. Never like touch it again. So let's do that. I will do that with a data class. It's not necessary. And I think immutability is nice for this kind of things. So something like named tuples would work well, since we are doing high compute. I don't know, like high compute workloads. Maybe you want something that's efficient. Named tuples are very compact since they are tuples. They are immutable since they are tuples as well. And yeah, they might be better than data class here. I'm just doing them because this, I don't know, maybe more cleaner or something. We can have slots here. It will optimize a little bit the memory, make it maybe even slightly faster. I'm not totally sure about how much we gain here, honestly, especially with Python. I think 3.12 and 3.13, I think it's already well optimized for this kind of things. So master address, master port, local rank, and we need the local word size. So for in a node, it will be, for example, 4. And for example, the local rank, this GPU here, it's rank 4 in the global rank, but it will be rank 0 in its local node. And let's use that. Maybe we can pass the whole identity and store it here and use it. Pass it here, identity, and so I will also change this one to use the identity instead. So here we added the local rank and local word size, but how do we actually compute them? So for that, the driver needs to know which workers are on the same node. Right now, we have no way to ask a worker which node is on, but we saw that here in UMI with hostname, we saw that we can get the node right. So we'll have a very simple method here, def get hostname self, and we'll return exactly this. So a hostname is just the name of the physical machine. Every node in a cluster has one, and the workers on the same hostname are on the same physical machine, which means they share NVLink, so fast GPU to GPU interconnect. This makes them very good candidates for like a TP group or something, since tensor parallel requires very heavy communication. And now in the driver node, in the driver code, we can build the identity. So we already, we have to create the workers first before we can send them an identity. And what need the master address, we need the master port. So just here, just before the distributed, we can ask for the host names. So for every worker, we're gonna ask for get the host name. I believe before I did forget this one, I think, and then I had to correct it. So yeah. And what we're going to do is, so we ask every worker for his host name, then group them by nodes. So we get a mapping from a physical machine to which worker indices are it. So we can do something like default list and enumerate host names. We can do host.band I. The grouping here, so I'm not totally sure, but I think the grouping here really depends on where array places the workers. So it can be a little bit arbitrary. So like when you go through this list, it doesn't mean that worker 3 will be placed in a node at the same node as the worker 0. So I think we can have like a different groupings, like instead of 0, 1, 2, 3, and then on one node, and 4, 5, 6, 7 on another node. I think it can be something like 0, 2, 4, 6 on one node, and 1, 3, 5, 7 on another node. I don't think we really control that. I think we can control that later on, but for the moment we don't. And what matters is that after this, we know which indices and which workers share a node. That's all we really care about that. And from that, we can compute the local rank, so a worker's position within its node, and we can compute the local world size, so how many workers are on that node. So let's do that. We can now have like the whole list of identities. Let's start with an empty list, and so this is our world size. The node, the local rank. So actually, these will be all the local ranks, and we can index in that one. So we know that the global rank is the same as our index in the loop. The world size is number of GPUs. The local rank, what we do is we look at all the ranks, the list of the ranks, the list of indices in this host or on this machine, and choose like what is the index in that list. And the local world size is going to be the length of local ranks. For in our case, all nodes have the same number of GPUs, but I guess in other cases you might have different nodes, different number of GPUs on different nodes. And the master address is almost a constant for the moment, for now. And that's it. So we can, instead of doing it that's distributed here, let me make sure that I'm using this correctly. Yes, so it can send the identity. And this should work exactly as before. We should get the numbers here. I'm wondering if I can showcase this without having to edit, but I don't know how much time it will take before printing. But yeah, we'll cut again and come back when I get the results. Back, as you see, this works. I had to fix a bunch of stuff. So here, identity.rank, I had to fix here to import the default dict, and I had to fix this one. I had identity instead of identities. So works again. That's perfect. So now that workers know their global rank and which node they're on, we can assign them a parallelism role. Example, with 2 nodes and 4 GPUs each, a natural setup is TP equal 4 within each node. Because tensor parallelism requires heavy communication and intra-node communication through NVLink is fast. And we can do DP equal 2 across the 2 nodes. So example, within a TP group, workers will split the weight matrices and each compute part of a forward pass, while across the 2 DP shards, each group processes a different chunk of the batch, right? The workers don't know any of this yet though, and all they can do, well, at least in our case, all they can do is a global AllReduce. But they can't do an AllReduce within just their node. For example, we need subgroups. And for this, we'll use torch.distributed again, but now we'll use dist.newGroup, which creates a communication subgroup from a subset of ranks. But there's a catch. It requires the global process group to exist first. So we can't you can't partition a world that hasn't been created yet, right? So with this, we already need it. We always need it. And then we can call new group to create subgroups. So let's do that. We can call it something like initialize or diff. So this creates it initializes like the distributed communications, and here we can call it topology. And what we need is node groups. We need all the groups that we have to create. It's very, very important because new group will new group will be called on everyone. So we can have something like for group ranks in node groups, new group rank equal group ranks. So here we will loop through every group and call new group for each one. Every rank must call new group for every group. even groups it doesn't belong to. This is very important because it's a nickel requirement because it's a collective operation. If rank say 5 here calls new group only for its own group and skips the others, then everything will hang. But for a given worker here, we don't care about much, we only care about its own group, so we'll save it. So if our rank is in here, we can save this handle to the group, and we can save this one as well. So here dist.new group returns a process group object, and it's a handle to a nickel communicator that we need for group operations. So that's why I'm saving it here. And this one here, why I'm saving this group, so it's different. So this is a process group object, it's different, and this will while my group will let me compute stuff like TP rank and the DP rank. So within my group, what's the, I should have this here as well. So what's my TP rank in my group, and TP rank is the index of my group in all groups. And we can also have this flag is collector, and it's only a convention here. It's only to get you familiar with like parallelism and stuff. You can have pipeline parallelism rank, etc. But yeah, and this is important to have intranode communication for the moment, and we'll use it and prove that it works similarly to before. We can have intranode, or maybe we can call it local. Similarly, it's gonna be exactly the same code, honestly. The only thing here that's different is just which group, and it's gonna be local group. Okay, perfect. My bad. And here we can have node groups. It's gonna be listed values. What did I call it here? Nodes. So nodes here is a dict. It has host name and a list of the indices of the workers that belong to that group. And node groups here is just a list of sublists, and every sublist is indices of workers that belong to the same group. We can actually print that. Hopefully we get into a case where like 0, 1, 5, 6 in the same node. And similarly as before, we can call it the same here. So just one quick thing here. I'm making a simplification where I say that one node equals one TP group. I mean, it doesn't have to be the case if you have, for example, 8 GPUs per node, and in this case, tensor parallel will give you, in this case, tensor parallel being 4, it will give you 2 TP groups per node. And what we want is for our code is to not care about that at all, and it's the case because what it does is it just loops across the node groups, and it creates the nickel subgroups for each and saves the one it belongs to. So this code generalizes, and obviously if you want to do pipeline parallelism or something more like you need like a pipeline rank, etc., you need to augment this method. But the worker here is not what we'll be using for reinforcement learning. It's just like an introduction to Ray, but everything here from worker identity to how we do stuff is what's important. So I will go and launch the script and get back when I have the results. I'm back. So I did make a couple of mistakes. So first here is rank instead of rank, which makes sense. Also I had indentation issues here. This one should be under this if else if branch. Totally makes sense. I mean, this is not even defined outside if branch. And most importantly, I totally forgot to create these subgroups. So but the results are correct. So in this group, the local AllReduce provides the correct number, and in this subgroup as well. So should show that everything is good and works, and that we are actually capable of making intranode communication as well. So similarly as before, we'll do a little bit of cleanup because similarly to our worker identity, because our topology is stored as bare attributes and it's scattered here across the worker. Where is it? So TP rank, well, actually TP rank it should be internal to the worker, but TP rank and is collector are scattered, and this one, well, it should be internal as well. But more importantly is that not only we don't want every worker class to repeat this pattern, we'll be having like an actor, critic, reference, etc. But since our workers will be different roles in the other pipeline, but more importantly is that for fused workers and for collocation, the same worker will be having different roles. So we can have like an actor and reference policy. It's like the same worker. And we'll be having a lot of this kind of attributes depending on the topology they are participating in. As we said, like it's different layouts, parallelism layouts, depending on whether they are training or not, stuff like that. And for the driver, it's gonna be harder to query the topology after initialization, because this representation here is just local to the worker, and the driver has no easy access to it. So what we want is a reusable piece, like some kind of registry of named meshes, and this is like similar to some things that you'd find in like distributed frameworks with torch, stuff like that. I think torch for example. And so we want a reusable registry of named meshes that a worker can hold on, and you can register a mesh for like every different role the worker can participate in. So for example, the actor for its groups, when it's doing the role of an actor, and then the reference, etc. And then from the driver perspective, it can just query them by name. And this is what we'll be doing next. So we'll replace the bare topology, which is just DP rank and is collector, with a composable registry that supports multiple meshes. And let's start with the information that we need. So as I said, it's gonna be very simple. We need the data parallel and whether it's the collector or not. And this is all. This is the minimal information we need, and I think it's also sufficient. Why? Because every mesh the worker participates in will get it needs this kind of information. And why? Because it captures the two things that the driver cares about. It cares about which data parallel shard this worker is in, and whether this worker is the one that holds the complete output or not. We don't need the tensor parallel rank because tensor parallel rank should be internal to the worker group. The driver doesn't need it at all. The driver needs to know how to split the data across different data parallel shards and where to collect the results. It doesn't care about the TP rank. It can also have like a worker can have like a pipeline parallelism rank, etc. And the driver doesn't really care about that. And that makes our code generalize easily by adding more when adding more parallelism strategies, because that's abstracted away internally in the worker. So from the driver perspective, it doesn't care about that, it doesn't know about that, so it's easy to add stuff to it. So that's it. That's all we need per mesh. Now we need somewhere to store them. So as we said, a worker might participate in multiple meshes, actor, reference, critic, etc., and each with its own DP rank and the collector. So we'll have a registry. That registry, I think we can create it here. The registry is gonna be very simple. It's just a dictionary and a dictionary wrapper, honestly, and it's just gonna have a name. And for every mesh name, it's gonna have like what kind of information. So let's create it. Gonna have a private attribute here. So this is what our meshes are, and they are gonna be like different meshes per worker. And we should be able to register a new mesh name, DP rank, and whether the worker is a collector or not. And we should be able to get the mesh information as well, so that from the driver perspective, and we I guess we're gonna see that it's gonna be easy to know which workers are collectors. So we just look through the workers, look at the mesh information, and get the ones that are collectors. So that's it. Very simple, and we're gonna create it here. Let's call it topology, and it's gonna be an empty mesh registry. I was thinking like where to put it. Definitely it should not be here in init topology, because this one will be called for every like for every new topology the worker gonna participate in, and it's gonna override this one every time. So in init distribution it's called once, and you create the mesh registry, and then every time you run init topology you should be able to register to this one. So what we're gonna do here instead is dev.topology dot register, and for the moment we're just gonna give it like some dumb name like custom worker, and we need the DP rank, and we need whether it's collector or not. So we can remove this, but this has to stay internal to the worker. So the way we think of this is init distribution sets up the infrastructure, process group, and registry, while init topology uses that infrastructure to register a specific mesh. And we'll have to update the driver code as well in order to use this thing. So for self.tp rank, it will stay on the worker. This needs it internally. We don't really use it for the moment, but maybe we'll use it in other videos. And the self.local group also stays on the worker because we need it here for this method. My bad, for this method here. And that's all we need. We can go and update our driver in order to use the mesh registry instead. Here we can come here and let's say mesh infos equal ray.get. We're gonna get for every worker, we're gonna get the info. What was it called again? Oh yeah, I need a method here to get the get mesh info and mesh name. Info, I believe it was called. So save the topology is a mesh registry, and it has this info method. It returns the mesh info. We can have that here. Actually, we can also have it here. Don't, yeah, okay, it's good. And in our case here, call it def mesh info, and we call it custom worker that remote. And this one, so it's gonna give us the DP rank and is collector for every worker. We can get all the collectors for enumerate mesh infos if that collector So I'm getting a handle to every worker and only the ones that are collector though. For collector worker, collectors, I can print there, who am I? Or yeah, or I can just have like something called def get identity, maybe return identity, that's important. This is just to print and show that it's indeed, like just to see what kind of, what it's called, get identity. So we'll go ahead, launch that and see whether all of this works or not. And as you see, we didn't require any modification for the previous code, so this is pretty good. And if we happen to, so one way to make this a little bit more general is just like to have a mesh name here, mesh name, and we can call it here mesh name. Change to that. We use a default value. And if we wanted to register different meshes for like different workers, we can have the exact same code as here. I'm back, and as expected, rank 0 here in this node is the collector and rank 3 here is the collector. So this works, and again, right now we only have one mesh called simple called custom worker. But if we think about collocation, we'll have like same GPUs to run different payloads, actor like training on FSTP layout, and then the reference policy inference with GP layout. So different parallelism, different groups, different DP rank assignments, etc. And this just makes it easier, and the registry pattern scales naturally. One more thing I wanted to talk about in this video, and it's something that has nothing to do, well, it's not going to be related to all of this, not going to reuse all of this stuff here, at least not for the moment. But something we've been ignoring is that all of this time we spawn the workers with this worker that's remote, and then Ray put them wherever. In our case, 4 GPUs per node means Ray has to put exactly 4 on each node. But we don't control which workers land together, and in general, with different node sizes or partial allocations, the split could be uneven, and we'd like to have more control about that. And one way to do that is what we call a placement group. And placement group is a resource reservation. And we can then have different strategies to place workers on these placement groups. Let's see how to do this. So we have to import the placement group function, placement group. We are also going to import the scheduling strategies. So both of these will show us like different ways Ray can place workers depending on the resources that it has. So the way it works is you ask for resources with placement group. You have to give it bundles and then the strategy. Let's see something called strict back. And our bundles describe what we want. So we know that we have 2 nodes and 4 GPUs in each. But for this one, let's ask only for like 1 GPU. Let's ask for 1 GPU here, and let's ask so 4 slots. So each slot will have 1 GPU and 1 CPU. This is just arbitrary, like we don't really care. So strict back here means that all 4 bundles, they must land on the same physical node. If no single node has 4 free GPUs, this fails rather than spreading. And we have to do it like this. That's ready. So this blocks until Ray has reserved the resources and the GPUs are now locked. No other actor can claim them. And the way to place workers using these slots is, let's say we have placement group workers. So we iterate across our bundles. We have this strategy, and for in our case, we have placement group called PG and placement group bundle index, which is this one. So placement group scheduling strategy takes two things: which placement group and which bundle index within it. And the way we use it is with actors, or like with our workers, we can have these options. So options, it lets you add stuff or override stuff. So here, scheduling strategy equal strategy, and we can call remote here. Let's save the handle to this, and we can print the results as before. See if I have this. We should see that they are in the same node. And notice that we don't pass like num GPUs in options because it's already on the class decorator. The scheduling strategy only adds a placement constraint on top, and they have to match, obviously. I mean, the bundle reserves the resources here. We reserve the resources, or at least say what slot has available. And the decorator here, it says what this actor, like what this worker needs or requires to work. So it makes sense for them to be compatible. So I will go and run this, and then we're gonna see other strategies. I'm back, and we can see that all of them are on the same node, though we have two nodes, and now we're going to try a different strategy, spread. And spread is what Ray is gonna try is to put each bundle on a different node. Obviously, we only have two nodes, so it's gonna put two bundles on different nodes. I'm back again, and we see that worker 0 is one node, worker 1 another node, worker 2 is on the same node as worker 0, and worker 3 is on the same node as worker 1. So this is spread, and there are other strategies. There is pack. So it tries the one node, tries to put everything in one node, and if not possible, it spreads. So it's less strict version of strict pack. And there is a strict spread, where it tries one bundle per node and fail if it's impossible. So it's the stricter version of spread. So that's it. And you see that this is a bit manual, and the driver has to manage resources directly and whatnot, create placement groups, pin workers to them, pin workers to bundles. And we'll extract that later on in another video into a resource pool layer, so the driver just declares what it needs and gets back workers ready to use. So that's it. Before we wrap up this video, let's step a little bit back and look at what we built. So the core idea here is that of the worker. So again, this is a very simple worker. It can be anything in your reinforcement learning pipeline or like roles. But the idea is that the worker doesn't know much about it. And it's important to abstract much away from the worker as much as possible, because the worker will contain our RL logic later on. And in our case here, our worker is just a process sitting on a GPU. It doesn't know if there's a training pipeline, it doesn't know where is the data, etc. So all of that comes from the driver. So the driver will be given the orders, and that's good because then it can hold the training pipeline and orchestrate different workers. And in our case here, we can indeed do that because the driver has the global view. Since it creates a worker, it knows topology and decides who gets what. And what did we give here to each worker? Like this identity, we give it an identity, so it allows it to know who it is in the world, what its rank, what node it's on, and also we give it a mesh registry. So what is its role in each mesh? So it's a collector, is it a DP shard, and then in this case, in our case here, we have some internal stuff, so TP rank and local group. This is internal to the worker, so we don't necessarily we won't necessarily have that in every other worker that we write, but the driver never sees that, and this split really matters. If we add more parallelism later, the driver code won't change at all, only the worker internals will get more complex. I think there is one edge case. So like, what does it mean that worker will get more complex? What does it mean? So if we add, for example, pipeline parallelism, it might change who is the collector because like a worker in TP group holds the full output, like it's more like a convention, but in pipeline parallelism, the collector might be the last pipeline stage instead. But that also fits in like in our code. Like we don't really need to change the mesh info. We don't need to change the mesh registry. All of that is internal to the worker. For the driver's perspective, it will just split the data across different shards and how internally within each like group, how the process of data is up to the different workers. So the best of the design is keep the driver-facing interface very narrow so that all parallelism complexity stays local to the workers while the driver writes simple sequential stuff. That's it, and see you in the next video.